Section 5.7 is just a review of the first 6 sections that we learned in Chapter 5. Each problem is going to ask us to factor, and it's going to use one or maybe two of the techniques that we learned when we learned how to factor in sections 5.1 through 5.6. My goal is just to be able to teach you how to look at a problem and to figure out what technique you need to use to factor it, and that's a tough skill to develop. So that's what my goal is for this section, is just to make it so that you can be independent of me and you can know how to factor a problem just by looking at it, looking for the key characteristics of the problem. And the first thing I should probably say is that if you're given a generic problem and you're asked to factor it, the absolute first thing you should do is look for any common factors. If there's a common factor, you need to get that common factor factored out first. If there is a common factor and you forget to factor it out, then the problem that you're trying to factor, it might not fit nicely into a category. The greatest common factor might obscure the factoring technique that you need to use. So absolutely, anytime I'm asked to factor, search for that greatest common factor and pull it out. If there's not a greatest common factor, fine, then the problem isn't obscured and you can jump straight into factoring. But if there is a common factor and you forget to factor it out, then you might doom yourself into not being able to factor or not be able to recognize the technique that you need. Ultimately, we factored problems with 4 terms, 3 terms, and 2 terms. We'll never factor with more than 4 terms nor less than 2 terms. The techniques that we learned were really based on, first, the number of terms, and if a problem has 4 terms, we're going to factor by grouping. I'll walk through the steps for factoring by grouping as we do the problems in section 5.7, but ultimately I just want you to think 4 terms, grouping. That's 99% of the time. If a problem has 4 terms in a higher class, grouping is a technique that you're going to want to use to factor. There are some really obscure techniques to factor problems that have 4 terms that you might see in higher class, but I don't want to jump into those now because that would just be too much, I think, at the beginning of learning how to factor. So 4 terms, grouping. In the world of 3 terms, how I factor is hinged or dependent on if there's a number in front of the squared term or not. Realistically, any problem that has 3 terms could be rewritten with 4 terms, and you can factor by grouping, but that's not the best practice. In the world of problems that have 3 terms, if there's no number in front of the square term, we're going to cite factor. Meaning, if I gave you a problem like if I asked you to factor x squared plus 2x minus 8, this I'm going to cite factor. I'm not going to rewrite it as 4 terms, and I'm not going to factor by grouping. Although I could, it's just slow and inefficient. When we get into the section, I'll review how to cite factor, but very specifically, if I'm given a problem with 3 terms, if after I factor out the greatest common factor, I'm left with factoring a problem that has 3 terms, and the only number in front of the square term is the implied 1, then I'm not going to rewrite it with 4 terms. I'm going to go straight into writing my answer. However, if I'm given a problem with 3 terms, and after I pull out any common factor, if there is a common factor, if I'm left with a number in front of the square term, then I'm kind of doomed. These problems I'm going to rewrite with 4 terms and factor by grouping. So 4 terms, I'm always going to factor by grouping. 3 terms, it's going to depend the technique I'm going to use and how the problem looks. If there's not a number in front of the square term, I'm going to use my template and I'm going to cite factor. If there is a number in front of the square term, I'm going to use my template to rewrite it as 4 terms and I'm going to factor by grouping. The other kind of problems that we factored had two terms. And in the world of two terms, there are squares and there are cubes. And if after I pull out my common factor, if the problem fits these criteria or these criteria or these criteria or these criteria, it's going to tell me how to factor. Ultimately, squares with minuses factor, squares with pluses are prime. So we're in the world of just examining problems that have exactly two terms. And in the world of two terms, the big categories are squares and cubes. And in the world of squares, we have squares with pluses and squares with minuses, or sums of squares and differences of squares. And in the worlds of cubes, we have cubes with pluses and cubes with minuses. Squares are evil because squares with pluses are prime, and squares with minuses factor. Cubes are not evil because cubes factor whether they have pluses or minus. So both styles of cubes factor. So I need to be able to, if I'm given a problem with two terms, figure out if it's a square or a cube problem, and then figure out if it's a square with a plus, square with a minus, cube with a plus, cube with a minus. What does it mean to be a square with a minus? Well, after any greatest common factor is factored out, to be a square problem with a minus, something that will factor, you need to only have two terms, minus sign between the terms. Variables have even exponents like 2, 4, 6, 8, 10, 12, 14, 16, and numbers are perfect squares like the numbers on the lists. If the problem fits all those categories, then the problem becomes a difference of squares and it will factor, and we'll revisit factoring these styles of problems in a minute when we get into the section. But this would be an example of a difference of squares or a square problem with a minus. It has two terms, has a minus between the terms, the variable has an even exponent, and the numbers 25 and 16 are perfect squares. A number is a perfect square if when I take its square root, I get an integer. If on my calculator I did the square root of 25, I get 5. So 25 is a perfect square because 5 squared equals to 25, or similarly, the square root of 25 equals 5. And similarly, 16 is a perfect square because 4 squared is 16, or we can say the square root of 16 is 4. So I need to be able to identify the categories of problems before I can put in the proper factoring technique. So differences of squares, two terms, minus between, even exponents on the variables, numbers are perfect squares. Differences of squares template factor, and they're easy to factor, and we'll get into the technique when we get into the section. Sum of squares, like if I just took this same problem but changed the sign, that changes a difference of squares into a sum of squares. To be a sum of squares, you need two terms, plus sign between, variables with even exponents, and the numbers are perfect squares. Sums of squares are all prime. The other category of problems that we have that have two terms are the cubes, and both differences of cubes and sums of cubes factor. So if we could identify a problem as a difference of cubes, or if we could identify a problem as a sum of cubes, it's going to factor. What does it take to be a difference of cubes? Well, after any greatest common factor is factored out, the problem can only have two terms, needs a minus sign between. Any variables have exponents that are multiples of 3, like 3, 6, 9, or 12. Should be a bullet point here, and that should be indented. and the numbers are perfect cubes like those numbers. This would be an example of a difference of cubes. 8x cubed minus 125. Why is it classified as a difference of cubes? Well, it has two terms. There's a minus sign between the terms. The exponent is 3, which is a multiple of 3, and the numbers are perfect cubes. Real specifically, to figure out if a number is a perfect cube, I should just cube root it. If I can cube root the number and I get an integer and not a decimal, the number is a perfect cube. If I cube root a number and I get a decimal, it's not a perfect cube. 7's not a perfect cube because when I cube root it, I get a decimal. 8 is a perfect cube because when I cube root it, I get a 2. And the numbers that I wrote down here are perfect cubes. So if a problem is a difference of cubes, it's going to factor, and that's the odd factoring. The first parentheses in the factoring gets one sign and two terms. The second parentheses gets two signs and three terms. The template for factoring differences of cubes are minus, plus, and plus. And we'll talk about how to fill in the parentheses when we get into the section. But now, just to be able to identify something, to categorize it is the big skill. If you can categorize it, then we can figure out how to factor it. If you can't categorize it, then figuring out how to factor it is hopeless. So differences of squares, sums of squares, difference of cubes, sum of cubes. The only difference between a difference and a sum is just the sign. So if I took this 8x cubed minus 125 and changed the sign, then all of a sudden it's now a sum of cubes as opposed to a difference of cubes, because the only difference in the criteria to be a sum of cubes compared to a difference of cubes is the sign is changed. Everything else is identical. Both differences of sum of cubes have the same number of terms, the same variables are permitted, the same constants and coefficients are permitted. In the world of cubes, both styles of cubes factor, and ultimately the only difference in the factoring are the signs in the parentheses. So that's probably as deep as I want it to get into theory, and then I'll go through the problems now and try to help you understand how to identify which style of problem it is, and then how to factor it once I identify it. So the first problems on my screen this morning are all two terms, and by glancing I don't see any common factors on problems 1, 2, 3, and 4. So I'm not going to worry about common factoring. And in the world of two terms, more often than not, if the exponent of 2 is 2, I think it's a square problem. If the exponent is 3, I think it's a cube problem. Problems 1 and 2 are square problems with a plus. They're square problems because the exponent is even, or the exponent is a multiple of 2. So to be a square problem, you need an even exponent, and any coefficient or constant needs to be a perfect square, which means if I do its square root on my calculator, I get a lovely integer. This is a square problem, and it's a sum of squares because of the plus sign between. So I fit the categories. I have two terms. I have even exponents. I have perfect squares for my number. And I have a plus sign between. This problem fits all the categories to be a sum, all the criteria to be a sum of squares. And all sums of squares are prime. So anytime I see a problem with two terms, my gut is to look at the exponent. If the exponent is 2, it's probably a square. If the exponent is 3, it's probably a cube. If the exponent is 2, and and there's a plus sign, then it's likely a sum of squares, which makes it prime. If the exponent is 2 and there's a minus between, it's probably a difference of squares. And it factors. Let me look at problem 4. It has 2 terms. In the world of 2 terms, we have to live with either a square or a cube. If the exponent is a multiple of 3, it's going to be a cube. If the exponent is a multiple of 2, it's likely to be a square problem. So exponents of 3, I think cube. Exponents of 2, I think square. So in this world, I see 2 terms. I see even exponents. And let me see if the numbers are perfect squares by trying to square root them. If each of the numbers, the coefficient as well as the constant, are square rootable and they turn into lovely integers, then those numbers are considered perfect squares. So in this problem, 2 terms, even exponents, the numbers are perfect squares because I can square root them. And there's a minus sign between. That makes this problem a difference of squares as opposed to a sum of squares. And differences of squares all factor using the template. The template is first parentheses gets a plus, second parentheses gets a minus. And I fill in the parentheses real easily. Before the plus sign, I take what's before the minus sign in the problem, and any coefficient I square root, and any exponent I divide by 2. So the 121, I'm going to square root it. The x, I'm going to divide its exponent by 2. Because the 121x squared precedes the minus sign, the result of square rooting the 121 and dividing the exponent by 2 is going to precede the signs in my parentheses. The 144 is going to turn into a 12 in my factors, and because the 144 came after the signs, the 12 that the 144 turns into is going to go after my signs. I claim that's an answer for problem 4 that's acceptable. The alternate answer would have the parentheses in the opposite order. Anytime I get an answer that factors into 2 parentheses, it doesn't matter which parentheses you put first and which parentheses you put second, as long as the contents of the parentheses are the same. The 4 problems on this page all appear to be cubes. There are 2 terms and I see exponents of 3. I think the problems are cubes. And for problem 6, if I look at this problem, it has 2 terms, which makes it for us either a square or a cube. It has an exponent of 3, which wouldn't make it a square. To be a square, you need exponents of 2, 4, and 6. To be a cube, 3, 6, and 9. There is some overlap between squares and cubes that the numbers should help us find. To see if a problem is with 2 terms is a cube problem, not only does the exponent need to be a multiple of 3, 3, 6, 9, 12, 15, any number needs to be a perfect cube, which means I should be able to put the constant or coefficient of any term on my calculator and cube root it and not get a decimal. So I see 2 terms, I see an exponent of 3, the number 1's a perfect cube, and there's a plus sign between. This problem number 6 is considered a sum of cubes. And the template for factoring sum of cubes, first parentheses gets 1 sign in 2 terms, the sign is plus. The second parentheses gets 2 signs in 3 terms. And the signs are minus and plus. I always keep the sign or put the same sign in. And then whatever sign I put in the first parentheses, I put the opposite of that sign to lead off my second parentheses. And my second parentheses always ends with plus. The acronym that we use for the signs is SOP, same sign, opposite sign, plus. To figure out what to put in the parentheses, under each factor or each term in the original problem, I deconstruct it into 3 factors that multiply to each term. For the x cubed, if I divide its exponent by 3, I get x to the first, and that tells me x cubed can be written as x times x times x. For the 1, if I cube root the 1 and get 1, that tells me that 1 can be written as 1 times 1 times 1. It's important to be able to write each of the terms in the original problem as the product of 3 identical factors. Once I'm able to do that, the first parentheses gets 1 from each group. The second parentheses, I form groups of 2 going in order. I multiply and put those in the second parentheses in order. So my first group of 2 was x times x. I led that off in my first parenthesis, second parentheses. The second multiplication I did is x times 1, and then 1 times 1, I put them in order in my second parentheses, and now I'll just do the multiplying. X times x gives me an x squared, 1 times x just gives me a 1x, and 1 times 1 gives me a 1. Claim that's a good answer for problem 6. Problem 8 is also a cube problem, specifically in the world of number 8. It has 2 terms again, and for us, a 2-term problem is either going to be a cube or a square problem. When the exponent is 2 and I have 2 terms, it's likely a square problem. When the exponent is 3 and I have 2 terms, then it's probably a cube problem. To be a cube problem, not only is it enough for an exponent to be like 3, 6, 9, and 12, any numbers I see have to be perfect cubes, which means I need to be able to cube root those numbers and not get a decimal. And that's the case here. So I have 2 terms, exponent of 3, the constant and the coefficient are perfect cubes. I have a minus sign between, and that's all the criteria to be a difference of cubes. In square problems, it's a big deal to know whether it's a square, sum of squares or differences of squares, because sums of squares are prime, differences of squares factor. In cube problems, it's not that big of a deal to know if it's a sum of cubes or a difference of cubes, because they both factor and the only difference are the signs. And if I remember the acronym SOP, then I can get the signs and not really have to fuss so much. So keep the sign, put the same sign in the first parentheses, and then whatever sign that I started my first parentheses, put the opposite of it to lead off my second parentheses. So that's the same sign as the problem, opposite of what I just put in, and then in the second parentheses, the second sign is always plus. Now I'm going to figure out what to fill up my parentheses with. I cube root the coefficients and the constants. I divide the exponents of the variables by 3. So the cube root of 27 is 3. X to the 3 divided by 3 gives me x to the first. The 27x cubed I'm going to think of as 3x times 3x times 3x. The cube root of 64 is 4. The 64 I'm going to think of as 4 times 4 times 4. Once I have my template and the values that go in my parentheses, I just start filling up the factoring. First parentheses gets 1 from each group. Second parentheses, I start taking them in pairs in order and filling up my second parentheses. My first pair is 3x times 3x. My second pair is 3x times 4. My last pair is 4 times 4. This step I usually don't show. Usually when I'm factoring cubes, I just go straight to the answer rather than showing the intermediate step that has the multiplying in the second parentheses left to be done. That would be a good answer for number 8. So we'll do 10 and 12 and then we'll move on to a part 2. For 10, I'm factoring with 3 terms. There's a number in front of the squared term. So this problem has 3 terms. There is no common factor. When there's 3 terms and there's a number in front of the first term, then I'm going to rewrite with 4 terms. And factor by grouping. If there wasn't a number in front of the squared term, I would sight factor. To get started on number 10, I have to multiply the 8, which is the coefficient of the squared term, times the negative 3, which is the constant. And I need to find the numbers that multiply to negative 24 and smaller number positive, bigger number negative, that add up to the negative 10. And just because I'm getting late on time here, I'm going to show these numbers for you without writing down all the possible factors. I claim these are the important factors that I'm going to need. I claim that these are the numbers that I'm going to need. 2 times negative 12 fits the criteria that the numbers multiply to negative 24, smaller number plus, bigger number minus. That's one of the criteria that's necessary. The second criteria is when I add those numbers that I get negative 10, which is the number that I haven't touched yet in this problem. So because the numbers 2 and negative 12 are the numbers that fit the criteria, smaller number plus, bigger number minus, multiply to negative 24, add to negative 10, I'm allowed to rewrite my negative 10y, and I'm going to rewrite it as negative 12y plus 2y. Now I'm going to take the problem, rewrite it as 4 terms. I like to write the negative first if there's both a negative and a positive. I like to give myself more room than I did, but I didn't. I'll have to live with it. Once I get the problem written with 4 terms, I need to split it in half. And I need to factor each half by using the greatest common factor factoring. The first 8y squared minus 12y, 4 is the biggest number that goes evenly into 8 and 12. So when I go to greatest common factor, 8y squared minus 12y, I can factor out a 4. And both terms of the 8y squared and the minus 12y have a y, so I can factor out a y. And I'll take the smaller of the exponents. So from the 8y squared minus 12y, I'm going to factor out a 4y. When I factor out a 4y, I divide by 4 and take a y away. I'm going to be left with a 2y minus 3. After my bar, there isn't a common factor between 2y and minus 3. So after the plus sign, I'm just going to put a 1 as my imaginary common factor because I need to have a parentheses after this plus sign. And when there isn't a common factor of the numbers or the terms after the sign, then I just assume there's a 1. And now I'm going to sneak out and finish my factoring. I'm going to put the common factor in one of my parentheses, followed by the factors in front of the parentheses in another. And when I go to write my answer, it doesn't matter the order that I write my factors in. The reason I want to sneak problem 12 onto this video is because 12 marries up so nicely with 10 that I can save myself a little bit of work. So for both 11 and 12, I think I used problems 9 and 10 to create them. Problem 12, when I look at it, it leads off with a negative, At a minimum, I know I need to rewrite this problem by factoring out a -1 because my factoring skills, my template for factoring problem with 3 terms doesn't work if the first term has a negative in front of it. In addition, in problem 12, the numbers 16, 20, and 6 are all divisible by 2. I'm going to factor out a -2 in problem 12 as my greatest common factor, which makes me flip the signs and divide by 2 when I go to fill out my parentheses. So as I go to fill out my parentheses, I'll take my signs and switch them. The -16, its sign is going to turn to positive inside the parentheses. The 16 I'm going to divide by 2 and get an 8. I didn't factor out a variable, so the x squared is going to hang out up front. The sign in the middle is going to turn to minus because I factored out a negative, and signs switch when you factor out a negative. The 20 that's in front of the x, I'm going to divide by 2 and get a 10 for my middle term inside my parentheses. And I'm going to leave the x because I didn't factor out an x. Last term in my parentheses, the sign is going to be minus because when I factor out a negative, I switch positive signs to negatives. I switch negative signs to positive. And the number, the 6 is going to turn into a 3 because I factored out a 2. I divide by 2. The reason I wanted to jump into my answer for this, if you look at what I'm about to factor, 8x squared minus 10x minus 3, and you look at what I just did factor, well, it's essentially factoring the same trinomial, except the variable's different. So I don't have to go through all the business of factoring that I just did. I can just steal the factors from problem 10, but change the y's to x's. And that should be a respectable answer for number 12 that could be checked. Again, time gets to be an issue, and I don't always check everything just because it's time. But on a test, time shouldn't be an issue. I try to give you ample time on a test, and checking is a great thing to do. So we're going to move on and do a part 2 to this video, and I don't think we'll do a part 3. We should be able to get it done in another half-hour chunk.